What's this?
It's called Cable. I call it Cable. It's K-A-B-E.
You almost ready to get started?
And you do data science. That's where they kind of got started. But you can use their web-based
So,
data science.
a couple quick announcements. A lot of you figured out that Buffalo Lab closed down their meetup group. So we moved to Buffalo Web Developer. So meetup.com will be using that group going forward, at least for the foreseeable future. Sorry there wasn't more warning. If you know anybody that usually attends, I don't have everybody's email address from Charlie yet, so if you know people that aren't here that might not be aware, just let them know. We'll also continue to use Twitter, Nextplex, and the Google group forum that we set up for scheduling. We're working on renewing sponsorship with Stark & Wayne and Engineer. If anybody has any other companies that would like to contribute, or anybody to suggest, let us know. The run rate is about $40 a meetup, but in reality it's actually much less than that, especially with Charlie's practice of returning cans and bottles. So we'll continue doing that because it's not a bad idea. Obviously, we're still running on our old sponsorship, so that was November last time. And we're just about to the point now where we're running out of money, so Charlie's done a really good job managing things, and he turned those funds over to me, so for now I'll be managing that. Charlie is doing a little bit better. He was suffering some pretty severe headaches, stuff like that. Still not at the point where he's getting out on his own and driving and stuff like that. And doesn't look like that'll be anytime soon. So he's looking forward to coming back and joining us for meetup, but he'll be undergoing treatment for a little while yet anyway. So I actually drove down and saw him, visited him with Tristan, and he was doing pretty good, but he gets tired easy. So we'll be looking ahead to April or May, possibly doing a meetup down southeast Buffalo, so maybe Orchard Park, maybe as far as East Aurora, depends on what the opportunity is. If we do that, are people still going to be able to attend? Like, let's see, show of hands for Orchard Park. Okay, East Aurora. Okay, cool. Obviously, if anybody knows anybody that comes this way from that area to come to our meetups, then could give Charlie a ride. That's always an option too. Want to try and make it accessible. Obviously, we're trying to record them so that Charlie can at least watch them later when he feels up to it. Upcoming meetups in February, I'm going to give a talk about efficient data. And with any luck, I might give that talk in San Francisco in February too. We'll see. And PJ is going to come talk to us in March about the rise of distributed databases. We're still open for April. April we might do lightning talks. Obviously we're going to try to schedule April, May, and June. We haven't had any proposals submitted, but we're welcoming anybody that wants to come and give a talk. That's about it. Turn it over to Oliver. Does anybody have any other announcements? All right, turn it over to Oliver. Is this on you?
I think so, yeah.
Okay.
Double check, there should be a red light.
Yep.
All right. Okay, so I figured I'd do something a little bit different this week. So I'm going to give you guys a math lesson. I apologize in advance, but this is actually something I find really cool. And if you find it cool too, the other kind of trend, the kind of trend that seems to be permeating many of the talks recently is it's an opportunity to shill a book. You should definitely look at this book. You may not know that the author is not me, but it's still an awesome book. It's both tasty and a really good explanation of some math that is way more obscure than it needs to be. Which is part of what I want to get at today. The original title of this talk was Category Theory, or How I Learned that Mathematicians Are Crap at Naming Things. So anyway, why does this belong in a database talk? Well, people always say that SQL is declarative. What does that mean? It means that I can take two different ways of phrasing the query, and the database is supposed to be able to figure out that the two are the same. So there's a ton of math behind this. I'm not going to get through that in half an hour, 45 minutes, or however long it takes me to go through these slides. But by the end of the talk, I at the very least want you to kind of understand on a really, really deep level why it's okay to take one of these queries and replace it with the other. The first one where I have a query that asks for rows of R where A and B are both 1 and 2 respectively, and the other query where I first ask for rows of R that are equal to, where A is equal to 1, and then I filter on B is equal to 2. Yes, this seems really, really simple. And just to make things even simpler, this is basically going to be the same thing as adding numbers.
By okay, you mean okay in the respect of it returning the same result?
Oh, yes, essentially.
Not necessarily okay with it from an
Some
administrative
optimizers
perspective.
some optimizers won't.
True, there are actually going to be some cases, one of which I'll illustrate, where this type of replacement is actually a good thing. Okay, anyway, the kind of heart of the matter, the other thing that I want you to take away from this talk is that basic arithmetic is really awesome. And I'm not kidding. I mean, there's some really amazing things that you don't really think about, but that are kind of just there. So for example, if you think of arithmetic, addition in particular, as a function, it's a function that you can take the parameters of and just randomly reshuffle the order in which they appear, and you still get the correct answer. You can randomly reshuffle the order in which you evaluate addition, and again, you get the same answer. And then there's this magical number 0. If you add it to any other number, you get back the same number that you started with. So mathematicians kind of see this and they go, wow, that is amazing. Let's give these things names. You probably recognize some of the names, commutativity, associativity, and maybe neutral element from high school, middle school math. But these are kind of patterns that appear a lot all over the place. And so, well, okay, this is database talk. Most people here are programmers, so I'll kind of rephrase this in a language that maybe you understand. But again, it's a function that you can reshuffle the order of the arguments. You can evaluate it in whatever order you like, and there's this magical function that you can value that you can call it on that basically turns into a no-op. So these are really cool properties, and as it turns out, these types of properties show up all over the place. So we've got addition, which follows these properties, addition over both natural numbers, reals, and imaginary numbers. But it also applies to Booleans. So if I take and, I can change the order of operations. I can reshuffle how I evaluate, and there's still a neutral element. If I and anything with true, I get back true. Same thing applies to or. And if you think about it, sets have the same kind of property. If I take two sets and I union them together, I get back the same set regardless of what order I union them in. And again, it doesn't matter what order I union things together, I still get back the same thing. There's other kind of magical functions that follow this property as well. Like if I take the minimum of some set, again, it doesn't matter, the minimum of 1 and 2 is the same as the minimum of 2 and 1, and I can apply this in whatever order I like. So, again, with the naming of things, mathematicians see this pattern and they go, wow, that's amazing. This kind of thing appears all over the place. So they decided to call it a group. Specifically, a group is what you might think of as an interface in Java or an abstract class in C++. So this interface, it takes some type, we're going to call it K, and it has two functions, or more precisely, it has some constant that you can call a 0, and it has some addition operator that takes two things and smushes them together, two of these K things and smushes them together. I'm going to jump back and forth between the Java notation and the way that mathematicians write this, which is a bit more concise, but we have some type, we have some operation, and then we have some neutral element. And this kind of thing appears everywhere. For real numbers, again, mathematicians can't really name things, but they use that funky little R for real numbers, natural numbers, Booleans. I think they have funky symbols for sets and multisets, but I don't know what they are, so I'm just going to write those out. But basically, there's a ton of different operations that follow exactly the same pattern. So, we can do some kind of fun things with this. I'm going to look at two of these groups in particular. One, the group of sets with union, and the group of natural numbers with the maximum being the function. So again, let me define this in terms of Java. This set group, the 0 element is the empty set, and then I can always take two sets and I can smush them together to get a new set by taking all of the elements of A, adding all of the elements of B, and returning that. Same thing with this maximum over integers group. If it operates over integers, and the 0 element is going to be negative infinity, but since we can't represent negative infinity in integers, we're just going to take whatever the minimum value is. And then we're going to add it, and in order to add it, add any two integers together, we're going to take their maximum. Okay, so I've got these sets, I've got these integers, and now I can define some sort of function that translates between these. So for example, I can define the maximum, a function that takes in a set, and it returns whatever the maximum value in that set is. I start off with minimum, loop over, find the lowest value, and return that. This is not especially efficient, but it works. So this setMax function basically takes as input one of these sets, and it returns one of these groups. Oh, sorry, one of these integers, or int_max objects. Now there's something really cool about this function. Specifically, I can call that function on the result of merging two sets together, or I could call that function on the result of one set, call that function on the result of another set, and get back, and then merge those two results together and get back exactly the same thing. So to illustrate this graphically, if I start off with an A and a B, I could first merge those two sets together and then take their maximum, or I could first take their maximum individually and then take the joint result of both. So this type of thing is another one of these patterns that mathematicians love, and like all things mathematicians love, they give them names. Mathematicians call this a homomorphism. So this basically means homo for same, and then morphism is basically what mathematicians call functions, or what category theorists call what we call functions. Why should you care about any of this? Well, let's take a look at two particular queries. One where we're trying to compute the maximum element from the union of two sets, and one where we compute the maximum of, first the maximum of R, and then the maximum of S. Anyone recognize this type of query pattern, or this type of optimization? Where have you seen this sort of thing before?
I used to work at a company that did a lot of database stuff, and we had a genius with SQL who could rewrite really hard queries to run efficiently on any platform, and she would do things like that to the SQL that none of us could figure out how she came to that, but it still ran faster by an order of magnitude than what was run elsewhere, because she was tweaking the optimizer through writing code.
Okay.
It's like common table expressions-ish.
A little bit.
Yeah.
So this sort of
It's just kind
query rewrite shows up all over the place in distributed databases. So to illustrate the point, if you don't have this sort of homomorphism-based rewrite that I'll go into a little more depth in a moment, you have a bunch of databases, and in a typical setting, these databases all have to basically compute some value and then send it to the server, or send it to the client to, let's say you're trying to compute the maximum of all of the values in tables on each individual node. Eventually that information is going to have to find its way all the way to one computer where that computer is going to do the heavy lifting, or essentially combine all of the results together. Now, without homomorphisms, basically that means we need to do all of the computation essentially in one place. All of the nodes have to send their data to the central server, and of course, most people here are looking at me like, what are you, crazy? Why would you send all of the data to the central server? And yeah, that basically would completely mess with everything. So what homomorphisms, and in particular that type of query rewrite, allow us to do is to convince ourselves that it's okay to first compute the maximum on for each individual server to compute the maximum locally, then send those maximums to the central server, the client, or wherever the final computation is happening, and then that client takes the maximum of the individual ones, and then everything's okay, and everyone's happy. So essentially what the homomorphisms allow us to do is prove to ourselves that these two computations are equivalent in terms of correctness. They both produce the same result, but we can find a version of the computation that is going to be way more efficient and more friendly to our computers. Okay, so we have groups, we have homomorphisms. Let's see what else we can do. Addition is cool. Multiplication is also really cool. It has a lot of the properties of addition. So it's commutative, it's associative, and it has a neutral element. In this case, it's 1. Multiply anything by 1, you get back the same thing. But now you can take addition, you can take multiplication. Oh, this, by the way, makes it a group. But you can also take addition, you can take multiplication, and you can combine them together. And then some really cool stuff comes out of this. For example, if you take the sum of two numbers and multiply it by something, you get the same thing as if you add the two numbers together.
Distributed?
Yes, actually. And there's also a magical, with multiplication in particular, if you take the neutral element of...
Is that the mathematical term?
Yes. Yes,
No, that's pronounced yes.
The Empire's been working on it for years. That's no moon.
You got a doctorate just so that you put that slide, right?
Exactly. Yeah, that's no...
It's no moon.
So the other kind of cool thing about multiplication is that if you take the neutral element of addition and you multiply it by anything, you get back the same neutral element, 0. You multiply anything by 0, you get back 0. And mathematicians love patterns, so we're gonna, so they look at this and they see, well, this kind of thing shows up all over the place. So you get it with natural numbers and real numbers in addition and multiplication, but you also get it with booleans. So once again, you can take or, you can take and then whatchamacallit? You can take or and, or anything with false and anything with true, and anything with false, and you get back false. And well, that basically follows the same set of rules. And it turns out that tables do exactly the same thing. Relational tables do exactly the same thing. Something we'll get into in just a moment. Right. So we've got groups, we've got homomorphisms. Now, the next kind of funky term mathematicians have come up with is semi-ring. This is related to groups. Don't ask me why it doesn't share a similar name, but it's called a semi-ring. I just go to Wikipedia to kind of figure out which of the 50 different combinations of features map to a particular name, but there you have it. This kind of pattern basically shows up all over the place, and in particular the one that's applicable to us is the fact that it applies to tables and queries over tables. So let me illustrate this with a little bit of data. We've got a couple of students, we've got a couple of courses, and now we want to know, for example, how many courses is each individual student taking. So naively we might do this by first taking the courses and basically getting rid of the course ID itself. All we care about is essentially the number of times that each student ID occurs. So we might start by just taking the student ID out of the courses table, and then grouping by that and counting up the number of course times that each student ID occurs. This type of representation is what is often called a multi-set or sometimes a bag, because it's a set in that every single tuple appears exactly once, but it's a multi-set because we have a multiplicity associated with each tuple. In other words, the row or tuple occurs, in this case, 1, 1, 1 occurs 2 times and 2, 2, 2 occurs 1 time. And kind of also implicit in this is not just that 1, 1, 1 occurs 2 times and 2, 2, 2 occurs 1 time, but that everything else occurs 0 times. Right, and because of the fact that everything except for a finite number of these rows occurs more than once, because only a finite number of rows occur more than once, we call this also a finite multiset. Okay, so then we take this courses table. We want to get the names of each student, so we join it with the names, and this slide is missing the names. Imagine that they're over there, but
Well, the query's missing it too.
yeah,
Sorry.
yeah, the query's got it.
Well, right, but there's no join there.
Yeah, you're right.
This is the mistake.
This is the magic of mathematics.
It lets you find when things are wrong. Yeah. All right. Imagine that this slide is right, and in theory, this slide is right. And we have this number here, this multiplicity 2, 1, 0. Where exactly do these numbers come from? Give me 1 sec here. So where exactly do these numbers come from? So this is a slightly update version of the slides. So let's do this the correct way. And our starting tables are SID. Okay, so now the question I have is where exactly do these two numbers come from? And the source of those numbers is actually quite closely related to the homomorphism relationship that I showed you earlier, except in this case, yeah. Well, okay. Let me start off with this. Why is that a 2? Because there's 2 records for it. In some sense that if that one row matches those 2. But why 2 specifically? And I kind of want to get into this on a really a little bit deeper. So let's start with this table and so that 2 basically comes from the fact that we have, as you say, 2 rows, and each of those rows occurs twice. Now let's say that Alice had taken this particular course twice. How would that change that 2? Or how would that change this 2?
Well, the count versus the sum that you query. If you want to know the value versus the number of rows.
Let's put this another way. 1, 1, 1, A occurs twice. Then it would be 3.
You're working on sets of sets.
Kind of. So essentially what's happening here is the reason that this is a 2 is because this row occurs originally once, this row occurs once, and 2 just happens to be equal to 1 plus 1. So by kind of getting rid of this one attribute, now these 2 tuples are the same, and we smush them together by essentially summing over their multiplicities. Here this only occurs once, and everything else occurs 0 times. So kind of the same thing applies here. It occurs 0 times there, it still occurs 0 times here. Okay, so now we've got 2 occurrences of SID 111, 1 occurrence of SID 222. And just to make things a little more interesting, let's say we also had SID 444 taking course A. Now that doesn't change the join result. Why? Or, well, let me rephrase that. Where does this 2 come from? Where does this 1 come from?
Count
The rows
the number
returned.
of rows.
Counted the number of rows. But let's say that, or is there a relationship between this number and, or what's the relationship between this number and this number? They're the same. Okay. So that seems to hold for Alice, that seems to hold for Bob. That doesn't hold for 444. Why? There's no name record. In other words, 444 for whatever goes to 0. In fact, everything that isn't explicitly defined occurs 0 times. So technically, there is a record for 444 over here.
What is
So
it?
maps to 0. Yeah.
Are we talking, well, I was just thinking about left joins and right joins. And what you've got there is a right join, right? Because we're going to select ones that have a name record. So the right join says, we can't take, the 444 doesn't count because we don't have a name for it.
Right, but that same thing holds for everything. So every row that doesn't appear in a table occurs 0 times. So 444 Dave occurs 0 times.
Okay.
So it's just a regular join, but in this case 444 has nothing to join with, and that in some sense means that 444 here joins with 444 here, but 444 doesn't actually occur. So whatever 444 joins with has a multiplicity of 0.
Okay.
Essentially what I'm trying to get at here is that the relationship between these numbers is once again it's not exactly the same number. Actually, let me change one small thing and then maybe you'll see where I'm going with this. Now, let's say there is a database error and Bob occurred. There are 2 entries for Bob in the table. Somebody didn't set their keys up properly. Bob occurs twice. What would happen to the result?
Still don't change because the count's based on the
Well, you can get that with querying on a non-key attribute too.
So the final query is join courses and students on the SID, and then count the number of rows in the result. So if I joined this table, so in other words, if I joined 111, 111, 222, 444, with 111, 222, 222, what would I get?
Bob will show up twice because he got too many records into the cell.
Exactly. So now that would become a 2. Because this 222 joins with both of those 222s, and now you've got 2 Bobs. So what happened? Where did this come from? And the point I'm trying to make here is that this number basically comes from the number of occurrences that 111 occurs on the left-hand side, and is multiplied by the number of occurrences of 111 on the right-hand side. And the same thing holds here. And technically, the same thing holds here. 0 times, or sorry, C times 0. And then anything times 0 is 0. So the kind of cool thing about this is that you can express pretty much any so the cool thing about this is that these multiplicities can be expressed by this. It's just out of order. Okay. A little bit out of order. Okay, so the cool thing about this is that I'm basically taking operations in a I'm taking operations from this semi-ring of natural numbers, multiplication and addition, and I can essentially express the behavior of the database using these operations. And the kind of cool thing is that I can define. Oh, here we go. I can basically define union as kind of adding multiplicities. I can define join as multiplying multiplicities, and aggregation, or in particular count-based aggregation, turns into the plus operation. The cool thing about this, though, is that I can basically take a variety of different semi-rings and plug in their addition and multiplication operations and get back different database behaviors. So, for example, if I plug in the natural number semi-ring, the one that I was talking about earlier, I essentially get normal SQL behavior. But then if I instead start talking about this in terms of, if I do the same exact thing, but instead of using plus and times, use or and, I get a behavior that is identical to what I get if I start using select distinct set databases, which were really, really popular early on until people figured out that they weren't very performant. But you get a variety of different behaviors just by plugging in a slightly different semi-ring into these into this kind of evaluation engine. You can get things like provenance. You can get things different types of permissions. There's been some work on getting differential privacy into this framework. And basically, these kind of three core operations, or these two core operations, can be used to express a lot of what happens in a database. Okay, so kind of tying this all back together, I said, well, why I tried to get across. I said I'd prove to you that those two queries I gave you early on were equivalent. So we have this one query here. I can define selection as basically this function that takes in one of these tables, and for any given tuple, it outputs a multiplicity of whatever it was before, as long as the corresponding attribute is 1 and 0 otherwise. And now that I've defined selection like this, I can apply selection over and over again because the output is the same type as the input, and essentially get and essentially get the original multiplicity if the A attribute is the same as the B attribute, or sorry, the attribute is 1, the B attribute is 2. Simplify a little bit and usually end up with the same query that, and essentially end up with the same query that I said was going to be equivalent. So hopefully I didn't discourage you too much from diving into category theory. Eugenia Wu does a way better job of explaining this than I just did. But there's just category theory. I've basically described to you kind of the fundamental idea of category theory, which is just finding patterns in everything, and finding patterns in all types of math. And those types of patterns help us see relationships between different types of operations, and those different types of operations expose a bunch of different optimization opportunities that databases can exploit. So yeah. If you're interested further, there's this wonderful book, How to Bake Pie by Eugenia Wu. There's also a really nice series of blog posts by Bartosz Chmielewski. There's the URL. Which explains category theory in a much more detailed way, kind of assuming that you're familiar with basic inheritance, object-oriented programming, and so forth. So yeah, I guess questions? Yeah.
Go back to that first slide where you had the two queries together. It's like 74 back buttons ago. Where we go into these two queries are essentially the same thing. With the queries that you have here, well, we've proved that. Where I'm at, I guess my question is okay, so great, knowing that bit of information,
How does
that make query number 2 somehow better, faster, cheaper, quicker than query number 1? Or so we've proven these two are equivalent.
Sure.
What is it that we can now do to make our lives better, quicker?
Okay. So the fact that these two are equivalent, and in particular the relationship, the process, the series of equivalencies that get us from one to the other, also give us the ability to explore not just these two equivalent queries, but all of the possible equivalent queries. And an optimizer is basically going to pick a couple of these equivalencies and just try them all out. It's going to try, it's going to estimate how much it costs to run this query. It's going to estimate how much it costs to run this query, and all of the other possible queries that it can come up with using these equivalencies. And at the end of the day, it's going to pick whichever one it thinks is going to run the fastest.
So this gives you multiple options then to pick which one is the fastest.
Exactly.
From an optimization perspective.
Exactly.
Cool.
To increase the complexity of your query by an order of magnitude in order to increase your performance, so.
Yeah, basically.
That's where the statistics on that information on the database impact the
I don't know.
query optimizer when it goes through that.
But you gotta update your histograms first.
Oh, shit.
And the lady I was speaking about who did this was specifically worked at a massively parallel database company. And so her
Okay.
entire thing was she would decompose it back into steps like this, because she understood what our optimizer was supposed to be doing, but wasn't capable of doing yet.
That's actually, so,
It's,
Make a patch
We-
much better.
you still run into that. We run on a large Exadata box, has 96 cores, and yet we still find it that we actually have to put in the hints at the optimizer at the query level to scale it back to 4 and 8 because it'll try to optimize and parallelize a simple process to 16 or 32 and cause it to run much longer.
Select
The-
one.
The optimize, yeah, so, the more, optimizers will sometimes, not try and explore the entire space. Because if you start adding more and more equivalencies, more rules that let you come up with new queries, what'll end up happening is, you'll spend more time optimizing, essentially that sort of scenario, than you actually do running the query itself. One of my colleagues encountered this with unions and case statements. So the Oracle optimizer will, if you have a case statement a couple of hundred levels deep, Oracle basically tries to rewrite that using unions, and the optimizer basically spends days running and never finishes.
See,
Sounds,
Don't do that.
Oh, yeah, basically. So what he did is write his own optimizer in front of Oracle, and then just told Oracle not to try and optimize that query.
At one point, I stepped out and go, what were you trying to do again?
it seems like some of the larger systems, even in SQL Server, that the large, core per socket model actually caused more performance issues because it tries to calculate the number of resources it has that it can break it into. And
Well, so a lot of these expansions are also going to have be relative to the number of cores you have. So, for example, the distributed example I had. Well, the distributed example that I had. You can think of this as basically computing the max of a set, you basically take in this one query and now you've broken it down to one big query and then 5 nested queries that each run on the individual nodes. Now that basically means that you have 5 times as many queries to optimize, or 5 times as many queries to explore. And that's one particular optimization. Now, for each of the optimizations, multiply it by 5, and you end up having considerably more, the complexity of the optimization could potentially grow exponentially with the number of partitions that you're trying to create.
yes.
Also, why you can sometimes do a lot better if you pre-optimize your query, or you optimize your queries offline, and then, I don't know of any database that actually will do this, but precompiled prepared statements can in principle be way faster because you can spend a lot more time optimizing. You don't need to necessarily run the query immediately.
You can do that with Oracle does that by storing the hash. You can store Oracle will store the hash algorithm of the query, and how you can then pin the optimizer, well, the way you want to optimize it, you can pin that into the cache. So therefore, when it sees the hash value come up again, it won't try to optimize it.
Yes, so, sorry, to be clear, I don't know of any database that will spend more time optimizing a prepared statement than it will process, just regular writing query.
Yeah, SQL has the same concept of pinning and plan that we use in execution plans.
Yeah, it will now, yeah.
So I have a question about, I've been working with primarily SQL Server databases, with a few others, including Cassandra, which is a distributed system, a little bit, but mostly SQL for a number of years. And the theoretical standpoint for me has always been set theory for relational databases. How related is this, if at all, some of it seems to overlap a little bit, but it's clearly not the same thing, so I'm wondering how that ties in.
So,
Could it be that the set theory is how you work with the database, and category theory would be how the database works with the database? I mean, that's how you do, that's the query optimization and so on, whereas set theory is more, these are the operations I want the database to perform for me. I'm
So-
a set of users, set of students.
so I don't have a great answer for you. The closest I can, what I can think of is set theory is essentially the theory of a very specific semi-ring, the set semi-ring. Category theory is kind of the broader class of stuff that you can work with. There's been a fair amount of work that essentially observes that you can think of databases as essentially a semi-ring. That's what I tried to get at here. That essentially unioning two tables is kind of like adding two tables, and joining two tables is kind of like multiplying them. And the observation is that you can essentially plug a variety of different semi-rings into that. And if you plug in the set union intersection semi-ring, you get set theory. If you plug the regular natural numbers addition multiplication semi-ring into that, you get bag semi-rings. You get bag databases, which is what SQL uses, what everyone's familiar with. And so essentially it turns out that they're actually quite, basically category theory lets you generalize past what database theoreticians have been doing for a very long time.
Is it, this is more applicable, not just to databases, but it sounds like it's also applicable to programming in general, too?
Yes, but I'd have to,
No, I know you didn't really get
yeah.
it, that wasn't the part of stuff, but it kind of sounded a little bit like, if you showed programming example
Oh.
where,
So basically what what mathematicians call a category, we would call an interface or an abstract class. And category theory is essentially the math of interfaces or the math of abstract classes.
Similar thought process, just implemented two different ways.
Yeah. It's all about abstracting patterns out of the things that we deal with. That's the subtitle of things and stuff.
Now, is there any relationship between category theory and all of like the ontology stuff that people do? I see some similarities, like the abstractions of abstractions that mechanism seems to be taking place in both, but maybe one.
I guess you could call category theory the ontology of math, but an ontology of math, but that might make a couple of people's heads explode, so I'm not going to say that. As far as I know, the answer is no, but I'm sure someone has thought of that before. I'm sure the answer is on the internet. I can't give it to you. Cool. So, once again, this is an amazing book. It really, this is up there with Godel Escherbach on my list of really, really accessible math books. Plus, it has some really good recipes for all sorts of things. My particular favorite is the recipe explaining exponential growth, because that is how you make puff pastry.
That'll be fun. Now what about barbecue?
Don't know.
Just gotta be one.
Yeah, I was gonna say. slowly.
That's for you to write.
Well, thank you very much. Thank you.
Thank you.
Thanks.